A very good afternoon to all of you. Let's start today's class. Today we are going to talk in two parts. In fact, we are going to finish the present chapter and we will start with the new chapter. Very little is left in the current chapter, so it's wise to start with the new chapter than wasting the time. And we can do this by having two YouTube links so that the two classes or two lectures are saved separately for later reference. I hope you all can see my screen clearly and hear my voice also clearly. If there is any difficulty in that, please let me know. So once again, a very good afternoon to all of you. Last class we spoke about the speech production, vocal tract, its features, etc. And today's class we were decided to talk about models of the vocal tract. There are various attempts made on the models of the vocal tract. Some of the models before electronic and software had helped us, these models were mechanical and fairly complicated. After the software, most of the modeling now happens using software. But nevertheless, it is very important to look at some of these primitive models so that we understand how the modeling work happens. So we talk about the models of the vocal tract primarily and look at some of the problems. Problems are not that challenging. Good afternoon, Pranav. So one of the simplest models of vocal tract is one tube approximation. So here in this model, we assume that the entire vocal tract is a single tube. You can see a single tube is over here. So entire vocal tract is a single tube. It is a pipe which is closed at one end by glottis and it is open at the other end by lips or at the lips end. Remember, open means your lips has to be open to keep the tube open. As you talk in general, the width of the tube changes, and if the lips are closed, it becomes a closed tube. Unfortunately, with closed lips, it's very difficult to talk. Although I have seen some of the mimicry artists, they do that wonder, but not possible for everyone. So open at the other end. We take the first model, very primitive, absolutely no link with any, for example, uh, for example, with the movement of the mouth cavity, you can change the width of the cavity. Here, not possible. Uh, Pulling in or pulling out the lips, you can change the length a little bit. Here, not possible. And of course, with the movement of the tongue, you can bring in the constrictions which are not possible. So it's a very fairly primitive model, but nevertheless it's very interesting model to study because it gives us an idea that how this model building happens. So we take a tube which is open at one end, closed at the other end, and what we normally do is, if you drive it with a speaker over here, small speaker. So if you want to do this kind of an experimentation, all you need to do is uh, you cover this entire you cover this entire section by a paper, this end of the tube, make a small hole in the paper at the center, and then you can keep the speaker of your headphone. So we all are having mobile, and we all have headphone hands-free cable here and there. So we can keep that the earplug or earphone of that headphone cable in this hole which you will be making in the paper. and that's how you can drive this air inside. On the other side, what will you do? So on the other side, you can keep the tube open. If you're at a relatively quieter place, then you can figure out the microphone hole uh, in the microphone hole in your this thing, um, in your mobile phone. Put that hole connected to this, or other words, take another hands-free cable and connect that to the mobile and find out where the microphone of hands-free cable is. You can place that small microphone here. There are many other ways also to do this. If you have some different kind of speakers and different kind of microphones, of course you are free to explore that. If you want to do this as a project work, I'm telling you, it's very interesting, doable, but remember, then these fluctuations in dB are very little. So all you have to do is, you know that the normal modes of vibration of this kind of tube is given by F is equal to NV upon 4L. Now, what are the parameters here? We are all familiar. V is the velocity of sound, L is the length of the tube, 4 is a number. Remember, the material of the tube does not matter here. As long as it is fairly smooth from inside, plastic tube, metal tube, cardboard, paper tube, etc. will do. N is the number of harmonics. It is a tube which is closed at one end. So we all know that the number of harmonics, odd harmonics will be present. Now if you drive this speaker with the signal generator, then what will happen is, you you will get first, if you start with a fundamental small frequency, then whenever the resonance will occur, the pickup by the microphone will become little stronger. So you will get a peak in the decibel level in the reading. This peak is very exaggerated in this diagram. Practically, it will not be that much. Typically, we stay in a very noisy environment. Normally, at your room, if you look at a dB in a quiet room, it is around 40-50 dB. Then if you do this experiment, you will find that it goes to around, on that base of 40 or 50 dB, it will go to around 55 or 60 dB. There will be slight resonance that will occur. So you have to be a careful observer to observe this. But it's fun. It's fun when you see those resonances happening. It's just exhilarating. So all you do is keep changing the frequency of the speaker. Start from a very low frequency and go at subsequently higher frequencies. You don't have to go to too high, because typically the length of the your entire vocal tract is around 17 centimeter, plus minus some 1 centimeter, depending upon the people, gender, etc. And the resonant frequencies will occur at 500, 1500, 2500. So you need, if you want to do this experiment, you can go up till say 3 resonant frequencies. So you change your frequency from say 100 hertz to around 3000 hertz, and note down the reading at every 100 hertz interval. So this will give you this interesting three peaks, giving you the resonance tubes of the resonance frequency of a tube closed at one end. We typically drive it to the pure sine wave for these kind of fundamental observations. But remember, vocal tract is more complicated. These are the resonances of the vocal tract. But if you remember in the last class discussion, and if you don't, then please, if you have not been in the lecture, please refer to the videos. If you look at the last class, we had discussed that the vocal folds are the seats of vibrations, and the vocal folds, they produce a typical vibrations which is a kind of a sawtooth wave with 8 millisecond time period, or the frequency of vibration of vocal fold is around 125 hertz. So typically the source of frequency is very the source of frequency in the human vocal cord vibrators of much lower frequency than the resonant frequencies of the vocal cord. So it is driven at a much lesser frequency and it is of a sawtooth wave in nature. So all we can do is we can drive this entire system instead of a sinusoidal wave. We can drive it with a sawtooth wave of around 125 hertz. So we can keep a round figure of around 100 hertz. Now bring in the Fourier analysis. If you bring in the Fourier analysis, you will find very interesting features over here. The sawtooth wave has got all the harmonics present. So sawtooth wave will have all the harmonics. So if this is a 100 first line, it will have 200, 300, 400, 500, 600. All the harmonics will be present. But you saw, if you have a pure sawtooth wave, then the harmonics decrease in amplitude. But not in this case. In this case, what will happen is the the original source, whatever source is generated, now its sawtooth will get multiplied by the resonant amplitudes. So if it has a higher resonance at a 500, then the 500 hertz frequency will become stronger. Then the 1500 hertz frequency will become stronger. Then there will be a dip. Then will be a 2500 frequency will become stronger. So you drive it with a sawtooth wave, all you will see is this kind of structure. And that's a very interesting thing. Heights of the harmonics are shaped by the resonances of the pipe. So now you are not driving with a pure signal, you are driving with a sawtooth. Sawtooth generates its spectrum, then you shape those heights, and this kind of is the origin of formants. Remember, I discussed in the last class that what are the formants. The formants are the groups of dominant frequencies in vocal cord. So it's like the vocal folds are providing the bass frequencies varying at a regular harmonic level, but some of those harmonics are amplified depending upon the resonances of the pipe. So that is the origin of the formants. You can do this also, an experiment. You can drive uh, the speaker by a sawtooth wave. You have to figure out a sawtooth wave generator, or Audacity will do it for you. And a sawtooth wave generator, you can drive the speaker by that, and this you can feed it to a spectrum analyzer. Spectrum analyzer are the free softwares available. The beauty of spectrum analyzer is that the once you feed the sound, it resolves it in the Fourier domain and gives you results immediately. There's a lot of calculation involved and they consume a lot of battery power as well. So see to it that when you're using spectrum analyzer, your batteries are completely charged or connected to the power supply. So that's how you do these kind of experimentation. So models of the vocal tract, this is a very simple model. Then people have tried complicated models also. So for example, if you want the sound of a, this kind of sound, then this is the waveform that you need. Remember, the fundamental has to be modified by this kind of waveform. So typically, if you have two tube approximations. One is a smaller, thinner tube having area A1, other one is a thicker tube having area A2, length D1, D2. Then this will have a sound. If you drive this with with your 100 hertz frequency sawtooth at the base, the sound generated will have this as an envelope. Remember, I'm talking about the envelope. This line, dotted line, is called envelope of the sound. So if you have a two pipe approximations, then you can have this. If you want a, then you can have this kind of approximation, the thicker one first, thinner one later. And if you want o, then you have two thicker ones and they are separated by a constriction. This is the envelope for frequency envelope for o. In fact, these formats are also a very interesting study projects. Last year in laboratory, we used to do the study of these formats. In fact, one of our favorite experiment was to speak in the microphone for at least uh, for three or four different vowels, A, E, I, O, something like that, and figure out what kind of sound is being generated, record it, figure out what are the dominant frequencies, find out the envelope. So this was one of the very important, interesting experiment. If you want to do it as a project, again, the idea is open. You can take five vowels, and I mean, you can ask everyone at home to speak into it, figure out that what are the dominant frequencies for each everybody, find out the average, and or see how do they differ or they similar, etc. So that's a two-tube approximation. Two-tube approximations have limitations. You cannot go much beyond in two-tube approximations. For example, if you want the sound of Z, then it becomes challenging. People have some more model. There is a general model with two tubes again, but with a restriction, and this restriction length varies sometimes. Overall length remains fixed at 16 centimeter, but the restriction length keeps varying depending upon what kind of things you want. There are other restrictions also. Sometimes the tube is made thinner or thicker, mimicking the behavior of movement of tongue inside the mouth. So even that is mimicked. Remember, in this case, this is mostly a tube which is closed at both ends. This is a tube, so it has the formula NV by 2LB, B for back tube, and the front tube is closed at one end, so MV by 4LF. And then these two tubes have a small, very thin coupling. So coupling actually distorts the frequencies. In fact, if you plot a graph of length of the back cavity with the formant frequencies, then typically how this is how the graph will look like. Dotted line, the back, and the solid line is for the front cavity. And normally what will happen is you will go up till here, and then there is a this small dotted line, so it's an overlap and it goes here. No longer remain as sharp as this. So these are the little advancement, but the models were of vocal tract. These kind of models of vocal tract were very limited in their appeal, in their flexibility, and last 30-40 years software has taken up this entire process. So the real-time analyzer, etc., everything is available. You can mimic the bass. If you remember the video I showed you in the last class, you can mimic the bass frequency, uh, and then you can modulate it suitably in software to create different outputs. So let's look at some of the problems. If you have pen, paper, pencil, please be ready. If you can give me some answers quickly, that would be great. If a person partially fills his or her lungs with helium and then speaks, Lord, I've never done it. The speech sounds distorted. It is sometimes described as sounding like Donald Duck. If you have heard about Donald Duck or seen Donald Duck cartoons, then you know that squeaky sound. hello Pluto, where are you? You know, that kind of sound. So this happens because if you fill now lungs is no helium is normally harmless gas, so helium balloons are available, and some kids sometimes do that they open the balloon and try to blow into it, but the high pressure helium goes in the lungs rather, and in that case, or if you want to do an experiment, you can do that. Be careful on your own risk, although there is not much risk involved. So what is happening over here is that you get a very squeaky sound. The question is why? Can anyone tell me? Explain this on the basis of formants. How the I mean, if I'm sounding this way, and if I'm getting a Donald Duck like sound, then I will sound this way. So what it means is that the formants are changing. The question is why? What would helium do? So would helium change I mean, how would helium change the frequency? You are moving normal. So actually the answers are straight, not very challenging here. It's a very straightforward. If you go back to the some of the Formula 1 tube approximation, etc., we saw that and this formula involves a velocity here. That's right, Atharva. So density of helium is less, so the speed of sound increase and the frequency increases. Pressure is largely same, remember, because lungs will have more or less at the same pressure, but the density suddenly changes. Helium is lighter, so the velocity of sound is much higher in helium. So frequency, the resonant frequencies will change not because the length is changing, not because n is changing, but it will change because v will change. The and therefore formants will change. I mean these peaks will shift. So these peaks instead of being here, it will be somewhere here at a higher side, and that will change the way the sound appears. Great. Second question. Calculate the first three resonances of a tube 11 centimeter long, the approximate length of a child's vocal tract, open at one end, closed at the other. So that's a very straightforward. We have seen it's a tube closed at one end. So you can write P V by 4L, and then the calculations are straightforward. You can write V, you can take V as 340 meter per second. So P as 1, so 340 divided by 4 into 11 centimeters, so 0.11. So 340 divided by 0.44 will actually give you your answer. 340 divided by 0.11, sorry, 0.44. You can see that this length is fairly small, and therefore vocal cord is the fundamental frequency will be fairly high. My calculations show that it is 772 hertz. I hope you get the same answer. Therefore, the fundamental frequency of a child would be at that value, and then the other three resonances are going to be at 3 times, so 2100, and 5 times, so 3500. That's right, 772, 2318, and 3863. Thank you, Atharva. So these are the frequencies at which the child children are going to talk. So remember, the children has very high frequency voice, high pitch voice, especially as they grow up, as the body length increases, the the vocal tract length also increases at around somewhere around age between 9 to 13. The length increases to its mature length of around 17 centimeter and the frequency drops. Express this in Newton per meter square. Maximum and minimum lungs pressure 4 centimeter and 20 centimeter of water. So lungs pressure experiment. I remember one student did a beautiful experiment in the college lab by which they had actually asked us to blow in a tube, U-tube, which was filled with water. And if you blow it hard, then the water level used to rise on the other end. So by looking at the difference between the water level in the tube, you can figure out that what is the lungs pressure, air pressure, or the pressure with which the lungs are applying on the tube. You can easily figure it out. So the calculation is very simple. It's rho GH. So you take the density of water into G into H. You will get maximum and minimum lung pressure depending upon what you are using. It's a manometer. Corresponds to atmospheric pressure is given, so you don't have to calculate. So that's a simple calculation. You can do it. So I will stop this link. We have finished this particular chapter. So stopping this over here.